In this video, I want to go through the basics of quantum decoherence. In particular, I would like to show you how we can easily explain the transition from a quantum system to a classical system. So, from a quantum behavior, we can see how a classical behavior arises. So, decoherence is important for that. So, in particular, in quantum physics, we have the so-called interference patterns sometimes that we see, for example, in the double slit experiment, and this interference occurs because we are in the quantum world. But if our system, for example, a particle interacts with the environment, so the environment is to be intended in a broad uh, way. So, for example, we might have a detector which detects which slit the particle goes through, or some other kind of system, some other kind of detector, and in general we can say environment that interacts with the quantum system, and that interaction will cause the interference pattern to disappear. So I want to show you some simple ideas behind what really occurs in this kind of quantum system. So we consider two waves. In particular, we have some function u1. So this is a wave that depends on just one variable x. For simplicity, we think that we are in a one-dimensional space, and this is of the order of an exponential I phi 1 of x. So we have a phase. This is a real phase that can depend on x. And similarly, we have a wave, a second wave that we call u2 of the order of an exponential I phi 2 of x. So the amplitude of the two waves is comparable, so they are almost of the same order. So we can say that the amplitude of u1 is 1 and the amplitude of u2 is 1, basically. But there is a phase difference between the two waves. And let's assume that we have a wave function which is made up of these two waves. And we define the wave function to be 1 over the square root of 2. And then we have u1 of x plus u2 of x. Now, when we want to see if there is an interference pattern, we have to take the mode squared of the wave function. So this would be like writing psi of x times the complex conjugate of psi of x. And if we do this, we have 1 over 2, and then we take the mode squared of u1, and we said earlier that we can take that to be equal to 1 because it's the mode squared of this exponential, so that's equal to 1. Similarly, we have the mode squared of u2, which is 1, so we have 1 plus 1 equals 2, but we also have terms of the kind u1 times u2 star, and then we have its complex conjugate, therefore u1 star u2. Well, if you take these two together, you get twice the real part of u1 times u2 star. And of course, the real part of this product is just the cosine of the phase difference between the two functions, phi 1 minus phi 2 or phi 2 minus y 1, because it's the same because the cosine is an even function. So we can also take the negative of this argument, it's not important. And of course, this gives us 1 plus the cosine of phi 1 of x minus phi 2 of x. So you can see that this square, which is something that we can take as an intensity that we see on the screen, for example. So we can take this as an intensity of the wave. So if the intensity is higher, then we have a greater probability to find the particle there. Whereas if this object here is lower, as a lower value, then there is a smaller chance to find the particle on the screen. For example, if we associate this function with a particle that hits a screen in a simple way, we can imagine this to be the case, but never mind. And you can see that the cosine can be either 1, its maximum value it can be 1, but its minimum value can be -1. So it can be 1 or -1 or a value in between. Therefore, this function can be 2. I mean, its maximum value can be, so it can be 2 because maybe phi1 minus phi2 is equal to 0. Therefore, the cosine will give us 1. And remember that this is a function of x. So it depends on the phases, this phase difference. And for example, that might be a value x such that the cosine is -1 and therefore we get 0, right? So in this case, we get an interesting effect due to the interference that we see here. So this cosine reminds of the interference between the waves. Now, at this point, let's also imagine that the initial wave function, so in particular, the initial wave function is made up of these two waves, and the two waves will evolve in space, and they might interact with the environment. So if they interact with the environment, we can we can approximate the action of the environment with two functions, chi1 and chi2, and I will explain how we can take this into consideration. But the environment will also depend on some parameter, for example, Q. So this is the parameter of the environment, and therefore these two are functions. This Q is the coordinate of the environment. And for example, chi1 might act on U1, whereas chi2 will act on U2. And let's take this and multiply by 1 over square root of 2, and we can take this to be a function. I will still call it psi for convenience, to remind ourselves that after all this is a wave function, but it's not the same psi as before. And this will be a function of x and a function of q. Now here I have simply sketched, I have simply assumed that the interaction between the environment and the wave is given by this product. You can be even more general than this, and instead you can assume that here you have a certain function f sub 1 if you want, of q and x, which depends on this parameter x, which for example can label the position of a particle, whereas q labels the environment, a detector or whatever. And so you might be more general. Instead of considering a product, you have a function of this kind. But for example, you might even expand this function in a Fourier series, and therefore you might still reduce this to a sum of products of functions of this kind, for example. But never mind. So the interaction can be more complicated than this simple product, but the behavior that I want to show you is still something that's useful to understand the basics of quantum decoherence. Now, at this point, what I want to do is I want to find a function, the I of x, and it's not the same function as before, but it's still a function that's reminiscent of interference, so of the interference pattern. And if we want to find such a function, we have to take the mod squared of our function psi of xq squared, and we have to get rid of the environment. So we have to sum over all the possible labels that the environment can take. So we have to sum over q, and this sum can be from -infinity to +infinity if the parameter allows all the possible values from -infinity to +infinity. But whatever. And another assumption is that the functions chi1 and chi2 are normalized with respect to the parameter q. So when we integrate over q, both chi1 and chi2, we get 1. So if we do this integration, of course, when we square this part and then we integrate over q, we are simply going to get the mod of u1 squared, But if you recall, the mode of of u1 square is just 1. So we get basically 1/2, which comes from squaring this. Then we get 1. And similarly, when we square this term and we integrate over q, we get 1. And then what are we left with? Well, of course, we have twice the real part of chi1 u1 times chi2 star u2 star. And here we also have to integrate over the variable q. Remember that. And let's rewrite it a little bit. So we have 2 divided by 2, which gives us 1, plus 2 divided by 2, which gives us 1. And therefore here we have integral of the real part of that. So we have the real part of, let's write chi1 as chi1. Remember that this can depend on q. And so we have chi1 written as the mode of chi1 times the phase. So we have e to the I, the phase. So we have, let's call it alpha 1 of q. And similarly, we can write chi2 star as mod chi2 of q times e to the minus, in this case, because we have the star. So we have minus I alpha 2 of q. Then we have u1 times u2 star, and that's e to the I phi 1 of x. So this does not depend on q. And then u2 star, we can write it here, minus I phi 2 of x. And we have to integrate over q, like this. So let's try to simplify this a little bit more. This can be written as 1 plus integral. So the real part will act on the complex exponentials. So we can rewrite it as mod chi1 of q times mod chi2 of q. So the mode of chi2 is the same as the mode of chi2 star. So it's complex conjugate, of course. And then here we have the cosine of alpha 1 of q minus alpha 2 of q. And then we have plus phi 1 of x minus phi 2 of x, like this. And then we have, of course, dq, written like this. Now, this is an interesting part at this point because you can see that the interference is given by this integral here. And if, for example, the mode of the two, let's call them waves, related to the action of the environment, if the two magnitudes are similar for are relatively constant as q changes, then we are summing these cosines. And if these phases are very different from each other, when we sum over all of the possibilities, the integral, this sum of cosines will go to zero. So it will be a small number if that's the case. But on the other hand, if this phase difference is constant, then we do not get zero, right? Not necessarily, because if, for example, this phase difference is just 0, then we can take this cosine outside of the integral, and then we have to sum over all these magnitudes. But of course, the sum of the magnitudes will never be 0. So you can understand that if we have, I mean, if the interactions are independent of each other, so independent means that there is no relationship between alpha 1 and alpha 2, so they are different from each other. And if these magnitudes are relatively constant over q, we can easily understand or intuitively understand that the sum of cosines will be 0. So it's due to this kind of independence of the two types of waves chi1 and chi2 interacting with the particle, if we call it particle, or interacting with the system. But on the other hand, if chi1 and chi2 are dependent, therefore, for example, alpha 1 and alpha 2 are, I mean, their difference is constant or relatively constant, then you might still have interference. And this kind of behavior is embedded into the concept of quantum decoherence. So whenever we let a system interact with the environment, we have this type of behavior which also describes the transition. I mean, the transition from a quantum type behavior to a classical type behavior. And this is just some kind of basic consideration. But there is way more to it than meets the eye, and I just wanted to touch upon the simplest concepts.